All right, this is Mr. Huebner, and currently in the isolation room at the North Pole. COVID. Hopefully I didn't ruin Christmas, so I think I'm pretty sure I'm negative. But what we're going to be doing today is bonding and shapes. Bonding and shapes. We're in the packet. It's green. I know it because it says it. And this is part one of 3 sections. We got a bunch of words here, and we're going to walk through this by doing a lot of examples. So first off, we're looking at the shapes of molecules in 3 dimensions. And I've got a simulation for the virtual option, and then for the face-to-face, we've got some fun little molecule linking devices that we'll be able to use. So it says bonding curves between chemical systems seek their lowest possible energy state. We've got a few terms. Localized electron model. So you guys can read it. It says a molecule is composed of atoms that are bound together by sharing pairs of electrons using the atomic orbitals of the bound atoms. In this model, electron pairs are assumed to be localized on a particular atom or in the space between the atoms. So so it's the localized electron model. It's what you've seen your sophomore year of chemistry. It accounts for 90% of explanations to bonding. So, and we'll talk about the other 10% in the other sections. We've got lone pairs and bonding pairs, and we're focusing mainly on covalent compounds where electrons are being shared. Ionic, it's basically stealing of electrons, so you don't really have a typical like a line bond. It's more or less just a plus and a minus, and it's a very strong electrostatic attraction. So when we're talking about all of this VSEPR model, valence shell electron pair repulsion model, hey, you might as well get that down. Yeah, what is VSEPR? Valence, which is outer, shell, electron, repulsion. Oh, I forgot P. P stands for pair. Valence shell electron pair repulsion model. Okay. All right, so we got bonding pairs and lone pairs. Let me just throw a picture out there for you guys. We got water, that's classic. We got right here is a pair of electrons. And here's a pair of electrons, here's a pair of electrons. Right here is a bonding pair. Pair of electrons, no, pair of atoms found in the space. Atoms? Oh my gosh. Good thing we're going over this. Pair of electrons found in the space between 2 atoms. All right. Lone pairs are pair of electrons not involved in bonding. Pair of electrons not involved in bonding. All right, so, and when you see the models or the simulations, it's a lot easier to visualize it. But here, taking a step back, doing this Lewis dot stuff, you guys probably remember this from sophomore year. But anything in column 1, these guys have 1 valence electron, so it's 1 dot. These guys have 2. Skipping these, we're not going to worry about those. We're doing these. 3 outer electrons, 4, 5, 6, 7, 8 outer electrons. All right. So oxygen, let's just look at oxygen. 1, 2, 3, 4, 5, 6. It's got 6 outer electrons, so it's going to be 1, 2, 3, 4, 5, 6. And then hydrogen is right here. It has 1 outer electron. And what I'm doing is I'm putting it where there's a single electron, and then they pair up. That's like the middle school way of doing it. I'm going to show you the high school way, or the IB way. Because this works just for basic ones, but we're going to do basic, medium, and hard. We're going to do all of them. So So normally this would look like a line. So you could do this. Some people mistakenly write it like that. That's not how it looks in real life, because what happens is you have these electron pairs that are next to each other. They're negative and they don't want to be next to each other. So they repel, and in doing so, they shove the bonding pairs of with the hydrogens down to make a bent shape. So that's kind of explaining this valence shell electron pair repulsion theory, is the lone pairs are creating these different geometric shapes. So it's all about the lone pairs. All right, here's a bunch of steps. So you'll catch on. It's a process. I don't know if I'll even go through it. I'll just speak the steps as we do examples. But it says count the number of valence electrons in the molecule. Remember to either add or subtract extra electrons when finding the Lewis structures. Let's just do examples. And what I'm in these examples, I'm just doing this process. And if you're doing a question on your own, you can go back to these steps. So look at this, Lewis dot structure examples. All right. So let me pick some examples. I'm going to do one example of each shape. Before we do that, we got a nice little chart right here that has all of the different shapes. And this is the hard part, is just memorizing it. So it's easy in the fact you don't have to do any mathematical calculations, but you got to memorize facts. So we got linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, and there's a different type of bent. There's two bents, one where you have one lone pair and one where you have two lone pairs, and the difference is the bond angle. One lone pair will repel it a little bit to make an obtuse 120 bond angle, 120 degree, but then if you have two lone pairs, it's going to make it more acute and push it down further to make less than 109.5. In order to get bent 120, it's got to be, you're going to have some resonance. So these are going to be trickier ones. The basic five are bent with the 109.5, two lone pairs, trigonal pyramidal, tetrahedral, trigonal planar, linear. Those are the ones that you learned your sophomore year in chemistry. We're going to do them all because this is IB. So including the expanded octet. The expanded octet is when the octet rule gets broken. Tricky thing about chemistry is you got all these rules and then you got exceptions to the rule. And the reason the octet rule can be broken, we'll talk more about it later, but in a nutshell, the d orbital allows more electrons to go into it, so you can have more than 8. So the rule is to have 8 outer electrons typically, but sometimes you can have more. If you're in row 1 or 2, these elements will not be able to break the octet rule. You will not see those elements breaking the octet rule, because if you add any extra electrons, it's going to go into the 3s, and in the third energy level there is no 2d. So basically argon, sulfur, so once you're in the third row, that's when you can start breaking the octet rule, because you have access now to that d orbital. Just a fun fact. All right. So there's bond angles, there's a shape name, there's what it looks like, number of lone pairs, and then electron groups. What this is talking about is, what is it talking about? So an electron group is a either an element that has electrons involved, like a bonding pair, or also a non-bonding pair, like a lone pair. So here we got 1, 2 bonding pairs, 2 electron groups. Here we got 1, 2, 3. 3 electron groups, 3 bonding pairs. Here we got 1, 2 bonding pairs and a lone pair. Still, it's 3 electron groups. That's kind of what that's talking about. All right, taking a page backwards. Got a whole bunch of examples. Let's start with linear. Let's put one right there. And gotta move my apple pie. Okay. Where are we? CO2. All right. So we got CO2. Here's an example. So the rule of thumb is figure out the central atom. And the central atom is ultimately going to be the one that has the most bonding sites. So let's do a quick example. Let's do lithium, beryllium. So lithium has one electron. Beryllium has 2 outer electrons. Boron's going to have 3. Can you see that? There it is. Sorry. Carbon has 4. Nitrogen has 1, 2, 3, 4, 5. Oxygen has 6. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And neon has 8. 1, 2, 3, 4, 5, 6, 7, 8. Alright, noble gases typically do not react. They're called inert, and that's because they have 8 outer electrons, and that's very stable. So they're good to go. Can they break the octet rule? Yes. So it's not common, but it happens. Alright, so out of all of these, which ones would be the best center atom? I'll answer it for you. The one that has the most bonding sites, 4 single electrons, carbon. That's why we got a whole section of chemistry called organic chemistry, which is a focus on the carbon atom, because it can form so many different types of molecules because of so many bonding sites. Boron has 3 bonding sites, and so does nitrogen, so those would be the next up. Beryllium and oxygen have 2 bonding sites, and then what's always going to be an outer atom would be the halogens with 1 bonding site, or in this case, lithium. Lithium, beryllium, boron are a little bit goofy because they're metals and typically form ionic compounds. Typically, lithium is going to be ionic. Beryllium, boron could be either or depending upon the situation. Like if you got aluminum chloride, that's a metal and a non-metal, you'd think it'd be ionic. But actually, the electronegativity difference of aluminum chlorine is within the 0.4 to 1.6 range, which is polar covalent. So again, chemistry has all these rules, and then there's exceptions to those rules, which makes it tricky. Alright, so back to CO2. C, we know, is always going to be the center atom, because it goes back to how many bonding sites. Also, another rule of thumb is the lesser amount. If you have just 1 versus 2, it's probably going to be the one where you just have 1 that's going to be the center. And we're going to do this, we're not going to do it the middle school way where you do the Lewis dot structures, connect the dots, because that only works for the simple ones, and most of them aren't going to be simple. So, according to the directions on the previous page, you're going to write both elements out, or all of the elements out, and you're going to connect them with at least 1 bond, because they're all going to be covalent that we're working with. And after that, you're going to need to figure out how many valence electrons are present overall. We got, oh, there's 2 oxygens. I got to put the other oxygen. So once you have your center atom, we're going with the basic ones that have a center atom and outer atoms. So carbon's the center. That means oxygens, all of them are going to be connected to carbon. Could you maybe have a situation where you have it COO, possibly, but those are goofy situations, not common. We're not going to be working with those. Alright, so they got to be connected to the center atom with at least 1 bond. I count the valence electrons. I know carbon has 1, 2, 3, 4 valence electrons. And oxygen has 1, 2, 3, 4, 5, 6 valence electrons, but there are 2 of them, so you multiply by 2, and this is going to give me 12 plus 4 is 16 valence electrons. That's just my shorthand for valence electrons. Oh, bummer, I don't think we're going to get to another one. We'll try to finish this one. So now I got to put dots around my outer atoms to make sure that they have 8. That's more important. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 6, 8, 11, 12, 13, 14, 15, 16, 2, 4, 6, 8. Hey, I used up all my electrons. I don't have any more. So these Lewis dot structures are showing just the outer electron arrangement. So I'm good with my actions, but carbon has 2, 4. I'm short 4. So in that case, sharing is caring, and it's going to be symmetrical typically. So this oxygen on the right is going to share 2 of them, and this on the right, on the left, is going to share 2 of them. I didn't gain or add or take away, I just shared. So we got 2, 4, 6, 8 for oxygen, and carbon now has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8 still, and it's all balanced. I used my valence electrons I have, and looking at this is going to be linear. Rule of thumb for linear is 2 outer atoms. Outer atoms. 0 lone pairs. And when I'm talking about lone pairs, I'm talking about on center. So 0 lone pairs on the center atom. None. They're all bonding pairs. But I do have 2 outer atoms, 1, 2, so it has to be linear. The other one that has 2 outer atoms is going to be bent, and it's bent because it has a lone pair on the center. So we'll get to that tomorrow. Oh my gosh, this is going to definitely take all day today, tomorrow, and Friday. So in the meantime, feel free to start on the reading assignment, and have a great day. Oh, okay, continue on. I thought there I was going to delete that whole video here. All right, so there we have it for linear. Next, why don't we do another type of linear? Because if you look on here, oh, there's another linear right there. Look at that. It's an expanded octet, and what we have is 2 lone pairs on the bottom and 1 on top, and they offset each other to basically make it back into a line instead of a bent structure. All right, so showing an example of another type of linear. Let's do I3 minus. Oh, this one's easy. I know iodine is going to be the central atom because it's my only option. So I'm going to have 1 I in the center, 1 I on the right, and 1 I on the left. It's kind of hard to do since I only have 2 I's. But all right. So, and they got to have at least 1 bond connected to the center. And next we got to do that thing, count the valence electrons. All right. Iodine is right there, and that looks like it's the 7A, so I'm going to have 7 outer electrons for that, and there's 3 of them, so that's going to be 21. Oh, wait a minute, there's a negative charge, which means I'm going to add another electron. All right, so it's actually 22 valence electrons. I already used up 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I always fill up the outer ones first. I got 16. 2, 4, 6, 8, 2, 4, 6, 8, that's good. I gotta get to 22. 17, 18, 19, 20, 21, 22. So what I do with my remaining electrons, I fill them all up onto the center, even if it gets me beyond 8. Because this is IB chemistry and we can break the rules. 2, 4, 6, 8, 10. So I got 2 extra on breaking the octet rule. Can I do that with iodine? Yes, because I have these d orbitals that I can fill up that allow me to do that. All right, so this is where memorization comes in, and if I have 2 outer atoms and 3 lone pairs, then it's going to be linear. 2 types of linear? Well, first of all, they got to have 2 outer atoms. So the only 2 options with 2 outer atoms is either linear or bent. 1 lone pair and 2 lone pairs is bent. 3 lone pairs is back to linear. So, again, memorization type stuff. So we're going to say 2 outer atoms and 3 lone pairs on center. All right, there we go. So that's linear, both types. Let's go back to simple. We got number 3. We'll do BF3. I think that's what, best friends forever? BF3. Boron's going to be in the center. Why? Because it's got 3 bonding sites. Fluorine has just 1. Or it's the one in least supply. Ooh, we got a question. Oh, I can't get to it there. Why is it 3 lone pairs in the center? For the iodine, lone pairs. So, because it's breaking that octet rule, because what we did was we added up all the valence electrons and found that it was 22. And if we just had 2 lone pairs on the center, the octet rule would be satisfied, but we'd only have 20 electrons. So we got to put those other 2 electrons somewhere, and where they go is in the d orbitals. And that's a little loophole to break the octet rule. So in certain situations where there are d orbitals available, like anything in period 3 or lower, then you can break the octet rule. So, but if you follow the process, then you can get there. No problem. All right, so we got BF3. Boron's going to be in the center. It's in least supply. It also has the most bonding sites. And I got to have at least 1 bond connected to each of the outer atoms. I got to figure out how many valence electrons I have. Boron has 3, and fluorine has 7. But there's 3 of them, so that's 21 plus 3 is 24. Valence electrons, I got 2, 4, 6. I add my electrons to my outer atoms first. If I got any left over, I add them to the center. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24. Hey, and I got 24. It works out perfectly. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But then I look at boron, it's got 2, 4, 6. What's going on with that? Well, it's another type of exception to the octet rule where you got less than 8. Anytime you got something in this goofy column right here, boron, aluminum, they're going to break the octet rule by not having 8. They'll have 6. And they're okay with that because it just happens to be stable with that arrangement. You could also have a situation where beryllium, these guys are going to have less than 8. And that is okay. Alright. Oh, what shape is this? 1, 2, 3. There's 2 types of trigonals. There's trigonal planar, and there's trigonal pyramidal. And you probably guessed it. What's the difference between the two? It's the lone pair on the center. If you plop a lone pair on the center atom, it's going to push down on all the fluorines and create a pyramid shape, which is why it would be called trigonal pyramidal. So we'll do an example of that. I don't know if we'll have enough time. Let's see. 3 outer atoms, 0 lone pairs on center. 0 lone pairs on the center. Okay, really, I should do NH3. So we'll write NH3, and then I'll leave this. We'll get as far as we can. NH3. Since we're talking about trigonal planar, I want to do an example of trigonal pyramidal. Again, nitrogen has the most bonding sites, 3 of them, versus hydrogen, which would have 1. And I got to connect at least 1 bond. And, oh, we can crank this one out. Yeah, this one's a simple one. So nitrogen has 1, 2, 3, 4, 5. And hydrogen has just 1. 1. But there's 3 of them. Oh my gosh. Okay. 3 plus 5 is 8. We got a total of 8 valence electrons. I got 1, 2, 3, 4, 5, 6. Then I got to add them to the outer. But unique thing about hydrogen, hydrogen has an energy level that's in the S. If we look at it, we got 1s2, 2s2. This is that electron configuration. Notice how the second energy level has 6, 7, 8. Octet rule. First energy level just has 2. Which means hydrogen and helium to be stable just need 2. So they're an exception. So hydrogen's perfectly happy just having 2. More politics. All right, we're done. No politics right now. Okay. All right. Yes, so hydrogen can only have 2, so that's happy. So it's 1, 2, 3, 4, 5, 6. We need 2 more, so we fill up the center because the outer ones are filled. And there it is. Look at that. It looks just like trigonal planar, but it's got lone pairs on the center. So this is trigonal pyramidal, and it has 3 outer atoms, 1 lone pair on center, and in hindsight it's looking like I didn't give you enough room, so apologize. We'll have to squeeze it in on a separate sheet somewhere. All right, that's all I've got. Well, actually, I got more than that, but that's all we got time for, unfortunately. So I will see you guys later.